In this video, we're going to explain data hazards in the Y86 pipeline, both how they arise and how we might address them. Note that the treatment here is specific to Bryant and O'Halloran's Y86 machine, but what we cover is similar to what you'd encounter with other ISAs. The Y86 pipeline contains the 5 stages shown here. Executing an instruction means moving through these 5 stages. In the fetch stage, we retrieve from memory the next instruction to be executed, that is, the one pointed to by the program counter, and break it into its component fields. The decode stage is where we retrieve from the register file the values of any registers required in this instruction's execution. In the execute stage, we invoke the ALU to perform any arithmetic and logical operations required by the instruction. We also set the condition codes, if called for by the instruction. And finally, if the current instruction is a conditional jump, we consult the condition codes to determine whether or not the jump should be taken. The memory stage is where we either read from memory or write to memory, if called for by the instruction. The Y86 ISA allows at most one memory access by any single instruction. Finally, in the write-back stage, the values of any registers modified in the execution of the instruction are updated in the register file. These are the 5 stages of the Y86 described by Bryant and O'Halloran in their book, Computer Systems: A Programmer's Perspective. One could imagine alternative pipeline schemes. However, these stages are very similar to those in simple pipelines for other architectures. Between each successive pair of stages is some sequential logic, or latches, to hold the values produced by the first stage and consumed by the second. Collectively, these are called pipeline registers. During a clock cycle, the combinational logic of each stage receives its input values from the pipeline registers feeding that stage and produces the output values that are latched at the end of the cycle into the pipeline registers feeding the following stage. Of course, the purpose of pipelining a machine is to improve the efficiency of execution. We have multiple instructions in flight at a given time, that is, passing through the stages of a pipeline. This means that less processing occurs on each instruction during a given clock cycle than would be the case for a sequential implementation, which allows a shorter cycle time. And it also means better utilization of the hardware, since hardware units in different phases are being used concurrently. But how do we know that the pipeline is correct? The answer is simple. A pipeline is really just an optimization. And as with any other optimization, it must not change the semantics of the ISA. This leads to an axiom, which we call the pipeline correctness axiom. A pipeline implementation is correct only if the pipeline machine implements the same ISA as a sequential machine. This means that any program that runs correctly on the sequential machine must run on the pipeline implementation, and the results must be semantically equivalent. Roughly speaking, this says that starting in identical machine states, execution of the program should result in identical machine states, whether run on the pipeline machine or on the sequential machine. Pipelining a machine introduces some challenges. Consider the fragment of Y86 code shown here. In a sequential implementation of the Y86, this code would not cause any issues. Each instruction would run to completion before the next instruction is fetched. So the state would be completely updated with all of the effects of the instruction before execution of the next instruction begins. But now suppose we have a pipelined implementation of the Y86 with the 5 stages we've discussed. Let's also suppose that the pipeline already contains some instructions, say V, W, X, Y, and Z, when we begin executing our program fragment. On the next clock cycle, each instruction in the pipeline moves ahead one stage. Instruction Z completes and leaves the pipeline. Concurrently, we fetch the IR move queue instruction and extract the various pieces of this new instruction, including identifying the destination register RAX. At the next clock tick, the IR move queue instruction transitions to the decode phase, and the add queue instruction is fetched and parsed. At this point, any register values needed by the IR move queue instruction are retrieved from the register file. In this case, there are none, since RAX is a destination, not a source. That is, the current value of RAX is irrelevant, since it will be overridden by this instruction. At the next clock tick, we advance all instructions one stage. The IR move queue instruction moves to execute, add queue moves to decode, and the XOR queue instruction is fetched. It's at this point that the data hazard is manifest. Recall that it's in the decode stage where we retrieve the values of any registers referenced by the instruction currently at that stage, add queue in this case. That means reading from the register file the current values of registers RAX and RBX. But here's the problem. The value of RAX should have been set to 50 by the previous instruction. And it will be, but not until that instruction reaches the write-back stage in the pipeline. That's where register values are updated in the register file. But the IR move queue instruction is only at the execute stage, still 2 cycles short of when that update will occur. Were the decode of the add queue instruction to retrieve from the register file the current value of RAX at that point, the value retrieved would be an old or stale value, not the appropriate value of 50. Such a problem is called a read after write data hazard, since we're reading a value after it ostensibly is written by the previous instruction, but before the state has actually been updated. If we allowed execution to proceed in this way, that is, to grab the value currently stored in the register file, it would violate our pipeline correctness axiom. A legal program would yield different results on the sequential and pipeline machines. We can't have that, so we have to deal with this issue somehow. Several approaches come to mind. First, we could simply reject pipelining in favor of a sequential implementation. However, this would sacrifice the very real performance benefits to be gained from pipelining, so we won't go that route unless there's no viable alternative. Second, we could imagine rejecting or modifying any programs whose execution would manifest data hazards. For example, the programmer or the compiler could detect read after write situations syntactically and insert sufficient no-ops into the program to delay the read until the write-back stage completes. That program fragment would look like this. This would solve the problem, but would violate our pipeline correctness axiom, which says that every legal Y86 program should behave the same on the pipeline and sequential machines, including our unmodified program. Third, we could program the pipeline implementation to detect read after write scenarios and behave as if there were several no-ops inserted. This is called stalling the pipeline. Consider the state at which the hazard manifests itself. At this point, we need the IR move queue instruction to proceed to write back so that the new value of RAX, namely 50, will be written to the register file and become available for the add queue instruction currently in decode. We can do that by stalling the pipeline at the decode stage. This means that the add queue instruction currently in decode stays there, as does the instruction in fetch, but instructions further along in the pipeline move ahead. In 2 clock cycles, the IR move queue instruction will reach the write-back stage and update the RAX register. On the following cycle, this update will have been completed, and the add queue instruction can complete the decode stage with the correct value and proceed. Thus, stalling for 3 cycles is guaranteed to preserve the semantics. This works fine, but introduces another wrinkle. When the add queue instruction is stalled, and the IR move queue instruction moves ahead through the pipeline, this leaves a gap in the pipeline. For 2 cycles, execute and memory are effectively idle. But those 2 stages are implemented via combinational and sequential logic, which must do something for those clock cycles. At the next clock tick, the combinational logic will read whatever values are in the pipeline registers feeding the stage and produce values for the pipeline registers fed by the stage. Those registers have to contain some data that forms a consistent snapshot of an execution state, as if they were legal instructions at those stages. This is handled as follows. When the pipeline stalls at a given stage, the hardware injects a bubble into the pipe at that stage. A bubble is really a virtual no-op. Operationally, this means that the hardware sets the values of those pipeline registers as if there had been a no-op in the program at this point, except that the PC is not advanced. That virtual no-op then proceeds through the pipe as any other instruction. Stalling is an effective approach to dealing with data hazards. However, it introduces inefficiency, since injecting those virtual no-ops consumes resources and reduces throughput. There's one additional way of dealing with data hazards that can partially eliminate this penalty. Recall our original code fragment. The data hazard occurs because register RAX is not updated with its new value, 50, until the IR move queue instruction reaches the write-back stage. However, that value actually is available after IR move queue passes through fetch. 50 is an explicit argument to the IR move queue instruction. It's passed from stage to stage in the pipeline and is recorded in the pipeline registers for each stage until it's finally written to RAX in the register file at the write-back stage. The pipeline implementation can be enhanced to take advantage of this fact and retrieve the value from some appropriate pipeline register several clock ticks before it's officially written back into the register file. In this case, when the add queue instruction is in the decode stage, the control logic can retrieve the value from the appropriate pipeline register rather than from the register file. This process is called forwarding. A needed value is forwarded from a later pipeline stage to an earlier stage before it's actually written to the register file or to memory. This eliminates the need for stalling the pipeline in many cases. However, there are still a few cases when forwarding cannot be used to resolve a data hazard. Consider this code, for example. Here, the source of the MR move queue instruction is a memory address. The value will not be available within the pipeline until after the memory stage. Therefore, forwarding cannot supply that value to the add queue any earlier than that. In this case, stalling is required. In a typical implementation of the pipeline, a combination of stalling and forwarding are used to deal with data hazards. Forward when possible, and stall when necessary.